Okay, welcome to our session 4. So today we are going to learn on support reactions, types of support reactions, idealization of structures. So as we all know, support reactions or this topic, support reaction is not new to you because you have already encountered this in your engineering mechanics as well as strength of materials. So we will just have a recap and review on what we have learned on that and then incorporate it on idealization of structures. Okay, so let us start with defining the support reactions. So support reactions are placed to a structure in order to prevent movements of members due to external forces. So if we have a structural system, we wanted to have movement restrictions. If we want is to restrict horizontal movement or a vertical one or even a rotation, we will use an appropriate support reactions to that structure. Okay, so if that is the case, the support reaction will absorb these forces or even the rotation or the moment. So the forces will have a horizontal and vertical translation, and of course, to prevent rotation, we have the moment. So we have here a table called from the book of Hibbeler, which summarizes the supports for coplanar structures. So for number 1, we have a light cable. So normally, a light cable supports a long span overhang structure like trusses or a beam, an I-beam that is having a long span. Okay, so what you do is to place a support to the edge in order to prevent further sag of the overhang. Okay, so what is the reaction? Of course, we have a cable. If we have a cable, remember that the cable supports a tensile load. Therefore, the reaction here is a tensile or tensile in nature. So an arrowhead that is going away from the member. So the number of unknowns is only one, that the parallel force on the cable itself. Okay, for number 2, we have rollers or rockers. So the rollers and rockers are free to move sideways because the reaction is only concentrated on the normal where it is resting. So in this case, this roller is resting on the floor. So what is the normal force on the floor? Of course, it is a vertical one. Okay. If our reaction is resting on the wall, of course, what is the normal to the wall? If the wall is vertical. If the wall is vertical, then the perpendicular force is a horizontal force. Okay, so that is the principle on roller or rocker. So on the side of the parallel to where it is resting, okay, it is free to move on that axis. Okay, so there is only one unknown. So again, the unknown here is a force that is perpendicular to the plane where it is resting. Okay, to the plane where it is resting, whether the plane is horizontal or vertical or even an inclined one. Okay, number 3, we have a smooth contacting surface. So similar, so this is somewhat similar to the roller or rocker. When a certain a certain structural member or a body is resting on a flooring or an inclined plane or any surface, there will be a single reaction that is normal to the surface. Okay? So another one, we have a smooth pin connected or collar. Okay? So this time, it is supported by a collar and a pin. Of course, the principle here is that the force has a vertical reaction or a single unknown that acts perpendicular to the surface at the point of contact. So when whatever the location of the point of contact, we will just have to uh, draw a perpendicular line to the point of contact of a smooth pin connected collar, and that will be your reaction. So only a single one. Okay, so for number 5, we have a smooth pin or hinge. So whether your member is inclined or in whatever position, there will be only two reaction, that is horizontal and vertical reaction. So what is the meaning of this? Although this smooth or pin is uh, rotated, or it is allowed to rotate whether clockwise or counterclockwise direction, it restrains or it restricts a vertical and horizontal movement. Okay, so basically there will be two unknowns here, and the reactions are two force component. So these two force component will have a resultant component that is the mother reaction of the smooth pin or hinge. So next we have also the slider. So slider, we have similar to the rocker or roller, only that it is restrained on the sideways movement, but it is also allows rotation, or we have here M. So there will be two unknowns, the reactions, force, and a moment. Okay, so basically the reactions here, as we can see, if this is the member or this is the wall, it is again perpendicular to the surface, but it is free to move up and down here, up or down here, and it is allowed to rotate. Okay, so finally, for number 7, we have a fixed support. So this is a common support for an RC frame or reinforced concrete frame, wherein we have a restrained support preventing movement horizontal and vertical, and preventing rotation. So it does not allow any displacement or any rotation, any uh, movement vertically and horizontally. So three unknowns, the reactions are the moment and the two force components. So here we have an example of hinge supports. So a hinge supports, we have bolt, rivets, or nails in lumber. So again, it is free to move or free to rotate. So it depends on how you treat the structure. So here we have a bridge structure that is free to move or free to rotate clockwise or counterclockwise, because this bridge is purposefully to elevate this one to pass the some boat transportation underneath the bridge. So it will open for the base, and then it will be closed, or it will be closed for the purpose of passing through this bridge. Okay. So for the hinge support, it is also used in swing door, because we need to swing it close. A closed swing and an open swing will have a hinge support for that, as well as for the framing of a certain building. If you wanted to have a fixed or hinge support, we will have a bolt connection and a welding. Okay, so another type of support, this is an actual picture of a roller or rocker support. As we have said, it is free to move this, or parallel to the support. It is free to move sideways if it is placed or on a horizontal plane. This is similar to the rocker. Why is it that we need to have that one? Because we have a thermal expansion for our bridges, as well as to have an allowance for a vibration or impact loads caused by a heavy load caused by vehicles or heavy trackings. Okay, so that is the purpose of a roller or rocker supports. So next we have the fixed support. So if we have a structural framing fully welded, then that will be considered as a fixed support, because does not permit any rotation, any horizontal or vertical displacement on the support itself. That is similar to the RC structure or reinforced concrete structure, because we have a sufficient anchorage on this uh, support, or a beam and column connections. So those are the fixed support. So we move on to the structural idealization. So the process of replacing actual structures that serves as structural model essential to structural analysis. Of course, when we perform structural analysis, we do not want to have a diagram or a model that is so complicated. So we wanted to simplify our structural model to come up with your analysis, right? Okay, so the process is just to simplify the actual structures versus the idealized structure. So in here we have a steel frame that is fixed connected here, that this is a sufficiently connected portion of a typical beam and column connection. So therefore, if we are going to have the idealized structure, it will be equivalent to this simply. Okay, so it is fixed at A, fixed at B, and as we can see here, we have already neglected some details of this hook. Okay, so another example is we have a frame, girder, and a column connection. So we wanted to have a framing system for that. We are going to have this as a line diagram here on top view, reflecting the columns at the corner edge, and then reflecting the girders here, and the beams as well as the joist. So as we can see in the line diagram here, this beam here is not fully connected to the girder, and this girder is not fully connected to the I-beam, I-column here, the implications of that one is that it is assumed that the connection is a pin or a hinge. Pin or a hinge. So basically, it is not a fixed connection. Okay? It is just placed as simply supported one. Simply supported, we have pin and a roller connection. So it is simply resting on this column. For example, for this joist and for this sub beams here, it is not fully welded to the girder, or even if it is welded, we can see here that we have only a single member here. So therefore, it is not assumed to be a fixed connection. Okay. Similar also to the girder and column connection, that is assumed to be a pin connection. Okay. So if it is a fully welded one, therefore we'll just extend the lines touching each other. Okay. That simply indicates that we have a fully fixed support for every connection that has a line connecting each other. Okay. So another example is if we have here a slab. Of course, in this slab we cannot see the structural framing system. We can indicate that actually on the idealist structure by a broken lines. So broken lines here simply means that we have a beam here, a vertical beam, but we do not have any transverse beam on that. Okay. So we have here a fixed connection. So we'll just have to indicate a top view for that. This is the I-beam. As we can see now, this line is fully attached to the I-beam, indicating that this is a fixed connection. So similarly, if we have an overhang beam here, we have here the fixed connection and a fixed connection here. Just the same, the line will be fully attached to the I-beam here on the top view. But if we have a hinge or pin connected support, we will just have a space here, or will not attach the line on the I-beam here. Okay, so that's the principle. So another example, we have here a block, and then on that block we have a floor stringers on it resting on the block or concrete hollow block, and then on this floor stringers we have the plank on it. So to indicate that in our top view, we would want to have a dotted line for the column or the uh, hollow block support, because it is resting on the bottom, and then the girder, we do not have any girder, so we have here the floor stringers are horizontal one. Okay, we have actually attached that into this block that is indicated with dotted lines. Okay, so how about if we have here a loading? How shall we reflect now the loading? So here is an example of a loading coming from the joist. Okay, of course, if we are going to apply a loading on the joist itself, it will be transmitted to a pressure on the concrete block walls that is directed oppositely to a downward force. So first, it will be converted into a certain pressure. Okay? Why pressure? Because this joist has a surface area, right? It is not concentratedly placed there. So in actual, it is not really a concentration of loading, but in actual, that could be converted into pressure, and then this pressure will be converted into a concentrated load. So as an equivalent model or idealized structure for that, it will yield to this figure. Okay, so from the force, convert it to the pressure, and then convert it to concentrated load. We have actually learned this on our prior lectures. Okay. Finally, we have here a comparison, an actual truss. It is connected by gasket plate, and it is fully weld. It has fully weld connections connected to a certain gasket plate. So it could be also connected by bolts or rivets on the joint to form a three-force member in a truss. So simply, we'll just have to indicate lines for that. Okay, not reflecting the plates, the installed plates. So these are the things that we need to know in our analysis. As soon as we will have examples for this. So I hope you learned how to idealize structures, and you appreciate our review on the types of loading and support reactions. Okay.